Hello, everyone. Actually, we are going to collect the questions, and then later we are going to post them on the website so that everyone can benefit, from these questions. Let me share the screen. Okay, do you see my screen?
Yes.
Great.
Yeah.
So I will start the first hands-on session of the day. Here is the agenda that you can find on this website. If you don't have the link to the website, ask it in the Slack or in Zoom, and we'll send you the link right away. So the first session is about hyperparameter search. So once you're on the website, you just go there and you have a button, and you just go right-click, open in tab, and you should have a Colab notebook that will open directly. Once you have the notebook, you will start the execution. So before starting the execution, we are doing hyperparameter search and character search. This requires some computation. So during the presentation, I will not execute live all the cells. I will execute most of them, but some of them I will keep them just to show you the output and explain. However, we encourage you, to start the notebook and see how it executes, how much time it takes. So in this notebook, we do hyperparameter search. On the problem of SST data, the goal is to predict the sea surface temperature. So let's start the first cell. The first cell is going to install the dependencies, and these notebooks can be executed on a local laptop or on Colab. That's why you have this detection of Colab. Most of the notebook of today will use the same use case, the sea surface temperature prediction. So once you follow the first hands-on session, the other presenters will skip the introduction part and directly go to what is changing with the different features of DeepHyper. Also, technical precision. It is not necessarily required to ask for GPUs or TPUs on Colab because we are using LSTM that is not always compatible with this optimization. So you can stay with the default configuration of Colab that is CPU-based and everything will be fine. So here the installer of DeepHyper is performed. After the installation, there is an important step related to how Colab is working. You have to restart the runtime. How do you do this? You go to runtime here, then you select restart runtime. When you click, you validate with yes, you wait for the runtime to restart here on the right. Once it has restarted, you execute the following cell. If you don't do this, some libraries may not be imported correctly by Colab. Okay, now that we executed the second cell, which is performing imports of softwares, you should see the DeepHyper version to 0.4.2. Now we can continue and dive into the data problem. So the first cell is loading the data, the raw data, where we can see the shape of the data is time step, latitude and longitude. So we load two data sets, training and test data, and we have the mask to have the mask over the continents because we just predict the sea surface. So if we visualize the data, we get the following, where the scale here is presenting the temperature between -5 and 35 degrees Celsius. Often in computational fluid dynamics, we perform dimensionality reduction. In machine learning, we call this PCA, principal component analysis. In CFD, they call this POD. We are going to perform this POD with 5 components. So we reduce the dimensionality of the data to 5. To do this, you take the map, you basically flatten the map, build a big vector, then you have a time step with respect to the variables, and you perform the PCA on this. After performing the PCA, you see that with 5 components, you already are able to save 93% of the information of the regional data, and it's reducing a lot the quantity of variables, of course. Now, if we want to visualize the difference between the original data and the reduced data, after reconstruction, this is what we have. So you can see, of course, that on the left, you have a lot more noise or low frequency information. On the right, it's a bit smoother because we keep only 5 components. The right one is the result of the reconstruction. Then we define the baseline LSTM model. So when you do hyperparameter search, neural active search, or any of this AutoML, often it's good to have a baseline model to be aware if there is a problem in the data. Because otherwise you may run an AutoML algorithm directly on the data, have a lot of results, but if the problems depend on the data, AutoML will not resolve the problem by searching for a model. Okay, so here, the baseline model, we define the default configuration of hyperparameters, which is the number of units in the LSTM layer, the activation function used, tanh and sigmoid, which are default parameters of the LSTM, the learning rate, the batch size, the dropout rate, the number of layers, and also the number of epochs to train the model. So we load the training data that are pre-processed. Then we build the model, the LSTM model here, using the input hyperparameters. Select the optimizer, the loss function, okay, and we train the model. Once we train the model, we return this model and its history. Let's execute the cell. Okay, works. We continue. It will perform the training of this model. So we see the loss is going down quite nicely. We don't seem to have a lot of overfitting, so the base result is not so bad, but you'll see we can improve. So here we look at the training curve of this model. We see again, we don't have overfitting and the loss is going down pretty well. Let's visualize with this baseline model what would give a reconstruction or prediction. So here we load the pre-processed data that were saved during the execution of the baseline model. Now we can perform a forecast. To perform a forecast, you can play with this number. We select 9 because it has to be at least strictly greater than the input horizon, which is 8. So input horizon is how many snapshots do we look in the past to perform a prediction. We take 8 in the past to predict 8 in the future. Here is what it gives. So we have the original data, we have the prediction in the middle, and on the right, we plot the absolute error, okay, between the original and the prediction. Now let's look at some metrics which help synthesize the performance. We can see that we have close performance on training and test. However, on valid, sorry. However, on test, we have a little worse performance. We use the R-square to quantify the quality of the training. And here we are able to reach on the test. So the generalization performance is 0.64. Okay, we will try to improve this, of course. So now let's look at what does DeepHyper, because previously it's basically using TensorFlow Keras to train a model. So now that we have a model, we can define a search space of hyperparameters. To do this, we go pull DeepHyper problem and we import hyperparameter problem. We build the problem. Once we build the problem, we can define the different hyperparameters. We start by defining the number of units. The number of units takes as default value 128 and can take value between 10 and 256. Then we can also define categorical parameters, which do not have ordering. Here we have sigmoid, tanh, and relief for activations, the default being tanh. We can also have continuous hyperparameters like the learning rate. But here, because we have different scale of values, we want to be able to explore uniformly all this size of learning rate. Therefore, we applied a log uniform transformation on the learning rate. Otherwise, we will add a lot more bigger sample than small sample in the exploration. You have the batch size, the dropout, the number of layers, and the epochs. It's always interesting to have default values of hyperparameters because you can infer this to the search so that the search is not going to start anywhere, but is going to start with your default configuration and try to improve on it. Then in DeepHyper, once you define the problem, you will define a run function. The run function is pretty simple. It is going to take a configuration of hyperparameters. This configuration is a Python dictionary. Then you build your model using this configuration. Once the model is trained, you collect the history and return an objective. Here, the objective which we want to maximize is the validation loss and the last performance. Using the last here is always important in training because if you use something before, like the best over the training, you may have overfitting effects. Using the last one is able to provide you with networks that keeps improving with time if you continue the search afterward. Otherwise, you may have learning curves that goes up, but are very good very quickly, but after they go down. And here we put a minus because, of course, the value of the loss usually is minimized in training, but we want to maximize, right? So here we do a minus to inverse the optimization problem. Then once you define the problem, the run function, how to evaluate the black box and the objective, you define a search. Here we import from DeepHyper search, hyperparameter search, the CBO search. The CBO search is the centralized Bayesian optimization search. To create the search, you just instantiate it with the problem, the run function. You can provide initial points to evaluate. So here we give the default configuration of the problem. You can log information into a directory. By default, it's the current directory, but here I prefer to define the directory with respect to my search. And here I fix the random state so that everyone here in the audience can have similar results. Then you execute the search. So I will start this cell, but it will take some time to be executed. When you execute this cell in a notebook, it will output you a warning. This warning is normal because in notebooks, you have the use of what is called async IO in Python, and we already also use it. And if we use it directly, basically the two backgrounds refresh mechanism, they interfere with each other. So when we apply dispatch, we create a different event loop in the background to be able to run DeepHyper in a notebook. So this is normal. And here you can see that it started to evaluate one model. So we will perform 20 iterations, okay? And this will tell you number of evaluations that failed because it's possible, and number of objective. The best one is outputted here. So here we retrieve the performance of the baseline because the first configurations to be evaluated is the baseline. Once the search will be executed, so it will take some time, so I will move forward. You will have the results that will be returned, okay? So the results, it's a data frame from Panda. It's the same data structure. And this will look like this. You will have first the hyperparameters for the columns, so activation, batch size, dropout, epochs, learning rate, number of layers, recurrent activation, units. Then you have a parameter, which is job ID. DeepHyper used this for centralized algorithm to determine in which order the configurations were generated and submitted to be computed. So here they are in the same order, of course, because we just do them one by one in the notebook. But if you were to execute many jobs in parallel, some will come back sooner than others, and therefore this order will not be like this. Then you have the objective, okay? So you find the objective, which is the value returned by the run function. And finally, you have two information, which is timestamp submit and timestamp gather. It refers to when the search started, and it tells you basically with respect to the evaluator, when was this configuration submitted and collected. Be careful, this does not correspond exactly to how much time it takes to evaluate the configurations. We can provide more documentation about how to make the difference about this. This is with respect to the evaluator, okay? So either if the evaluator submits, but the job is not directly processed to be computed, this is where the difference can happen. Okay, so now that you have this result from DeepHyper, we can look at what was the best configuration, right? So here I'm not executing the cell because the the search didn't finish, but basically I just select the argmax of my data frame and I look at the best configurations. And this is the best configuration of hyperparameters that was found. And now that I have these configurations, of course, I can build my model, train it, if it was not checkpointed during the search, and see how it performed. So this is what we do. We reuse the same function, infer the best configuration of hyperparameters, and continue. So the model is trained. Let's look at the learning curve. The learning curve is showing you that the best model found by DeepHyper is better than the baseline. Okay. So the number of epochs, remember, was an hyperparameter. So here I choose to increase the number of epochs, which makes sense. But also we can see that even if we train for a smaller number of epochs, we were still better. Also, you can see that there is no overfitting, so you are quite happy. It's good to mention in hyperparameter search that you have three splits in your data set. You have the training data, which train your model, the validation data to select your model, and the test data, which you use just to evaluate generalization performance to avoid bias. The validation data set has to be big enough or representative enough of the training and evaluation data set to avoid overfitting. For example, if you have imbalance in your training data, be careful about how you do these splits so that you have the same quantity or same ratio of imbalance in training, validation, and test data. And also validation has to be big enough if I didn't say it yet. Then we continue. We take the best model here and we plot a prediction. And we see that the absolute error is lower than before. Here we have -5 as the maximum error. Before, if I go up a bit, we're having -7, I think. Yes, -7. And we have a bit more brighter values here. Okay. So we do less errors, so it's quite nice. And we can see also that we move from 0.60 something to 0.89 in performance on the test set. You still have a discrepancy here between train, valid, and test, which is normal because the problem is framed so that we trained in the past, we validate a bit in the future, and the test is the most recent data. So the more you move away from your initial data, the more you have distribution shift effects with time series. So this is why this is happening. But we improved a lot, the performance from 0.6 to 0.8, almost 0.9. Now, in HPC, there is a key feature that everyone wants to have. It's checkpointing. When you run hyperparameter search on HPC system and the job fails for whatever reasons, in DeepHyper during the search, a local file called results.csv is stored in your file system each time it collects new configurations that are finished. You can retrieve this file here when you want to restart a search from another runtime. So you just, for example, here I define another logging directory to make the difference and not override the previous file, of course. Then to infer the previous execution, you just have to do search fit surrogate. You give the path to the file. This will load the CSV, train the surrogate model, and after you can continue the search. Let's see if this does something. If we look at the output here, you can see that from the start of the search, where we just do 10 evaluation, it already selects TANH as activation function. Similarly, the learning rate is almost at the same order of magnitude, right? And the number of layers is almost always fixed to 1. If we compare to the previous results, this was very different because we got initially some expiration. So you can see the activation function was changing, the learning rate was also changing more, and the number of layers was also tried differently as well. Okay, so this is how you can check that the checkpointing was correctly inferred. We are done with this notebook. If you have questions, maybe I think we have 5 minutes where participants can talk directly with us. So I encourage you to ask a question live, and I will do my best to answer you.
Hi, I have a question on in an HPC setting, and I don't know if it's covered later. Just tell me it'll be covered later. But is there the capability to start up individual training jobs on like a Slurm script and have that job return to the overall search, or does this all have to be run kind of within the same process without any capability for that type of stuff?
So I'm not sure to understand really the question. What I can tell you is DeepHyper is used with different type of schedulers. At the ILCF, for example, we have a Cobalt with a QSub, but it's also used with Slurm. Okay. Here in notebooks, something that is key is that we directly pass a run function. So because we are in a serial context, execution one by one, you just pass your black box function and it executed one evaluation after the other. However, in this software, we have an object which will be explained later in HPC demonstrations for DeepHyper, which helps you parallelize the execution with different type of backends. You can have a process, you can have thread, you can have subprocess, you can have RAID, you can have MPI. Okay, you can also define your own backend if you have a specific use case, and therefore this can be run. For example, a user submits a Slurm job. Okay, and two ways of executing it. You have the Slurm job that directly asks for a number of MPI processes. Okay, and the search will execute in rank 0 and use other ranks to perform evaluations. Okay. So this is the most classical way where this can be used.
Okay, and
so
that will be
your
covered.
question is on like, okay, so do you want to generate for each evaluation a Slurm script and submit that as a part of like job submission process?
Yeah, that's kind of what I'm thinking.
Okay.
I mean, that's what I do now in the primitive grid search that type
Right.
stuff. So yeah.
I mean, I have seen people using GNU Parallel and things like that, generate a script and then submit that to the queuing system and run it. So more like, each evaluation is a separate job. So right now, what we are doing is more like, one job, you take n nodes and we want to keep n nodes, always occupied, right? So that's a thing. But as Roma mentioned, you can write your own backend in this case to generate a script, right? So all this, take this configuration and then generate a script, and you can submit that as a job as well. So the backend is extensible, and you can use in the way that you just described.
Okay, great.
So
thank you.
I will use this to show the best website that you can use to check a bit the features, the documentation. Okay, and with respect to your question, it's called the evaluator in our framework. Okay, and when you have an evaluator, you have the base class evaluator. It's what's going to distribute the execution. You just have one function to implement. The function is called execute. And in this execute, you develop the fact that you submit to the job scheduler. There is no problem. After, you can directly parse the result, the output, and return this, and it's quite easy.
Okay, I see that. I guess maybe this is too in the weeds, and I just need to read the documentation. But is there any capability? Because and the reason I'm asking this is because a lot of nodes will have 4 GPUs on them, so it doesn't make sense to just submit one job per node. You want to like give it a minimum 4 jobs to try it once. Is there any capability to kind of chunk executions that way here?
I don't understand. For example, right now in Theta GPU, we have many nodes and we have many GPUs per node. We have 8 GPUs per node and up to 20 nodes, for example. You can directly submit on this, have the search run in one, and because it will execute asynchronously, you will have your result faster, and it's using the nodes properly. So as soon as the job on one GPU is done, it collects the results and it fills it back. It doesn't wait. Okay, so that's how we use efficiently the resources. So you can directly use all GPU, one GPU per evaluation.
So Ian, is your question on like, okay, so you have multiple GPUs you want to leverage, or you want to chunk up each GPU multiple workers?
I want each GPU to function as one worker training one model at a time. But obviously I want DeepHyper to manage spinning up these jobs and then.
Yeah,
that's straightforward. That's
Okay.
by definition, right? You say, okay, so I have 4 GPUs, you can set 4 workers, right? And 1 worker per GPU, and there will be 4 model training happening at any given point of time.
Okay, great.
This will be covered this afternoon in the running DeepHyper at scale. You will see example of how to do this.
Okay, perfect. I'll stay tuned for that.